Parabola sheet 1 subjective. The first problem, there is a point P, a moving point P, right? And a pair of tangents are drawn from this moving point P. This is one tangent, this is another tangent. To a parabola y squared equal to 4ax. And the slopes of these tangents are m1 equal to tan theta 1. For different positions of P, you will have different values of theta 1, right? And the slope of this tangent is tan theta 2. Theta 1 and theta 2 are parameters, right? The point P is a moving point, let's say having variable coordinates h comma k, right? These are variable slopes, but they vary subject to a condition. What's the condition? Theta 1, theta 2 can vary, but we must maintain cos theta 1 into cos theta 2 equal to a constant mu. Such has to be the discipline of variation of theta 1 and theta 2. Okay. Now, given this, we want to be able to find the locus of this moving point P, one that moves in a manner that cos theta 1 into cos theta 2 is preserved, right? So, what are the parameters in this situation? Theta 1 and theta 2. For different positions of P, you will have different values of theta 1 and theta 2, but only those positions of P would be regarded sanguine for which cos theta 1 into cos theta 2 is a constant mu, right? So we want to eliminate theta 1 and theta 2, we want to connect h and k and then generalize, replace h by x and k by y, which will offer the locus of the moving point P. Clear? Now, look, any parabola, any tangent to this parabola must be of the form y equal to mx plus a by m. Any tangent to the parabola must be of the form y equal to mx plus a by m. Now, if this tangent passes through P, the slope of the tangent would be m. And if this tangent passes through P, right, h comma k, then it must satisfy this equation. K would be mh plus a by m, right? Now, if you solve for m, what would you get? You get the slope of the tangent drawn from hk to the parabola. If you solve for m, what would you get? You get the slope of the tangent drawn from hk to the parabola. That's what you get. Now, which then is like h into m squared minus k into m plus a equal to 0, right? It gives you a quadratic in m, implying therefore that two slopes means two tangents from hk to the parabola. One tangent from the point hk to the parabola would have slope m1, which would be one of the roots of this equation. The slope of the other tangent would be the other root of this equation. The roots of this equation would be the slopes of the two tangents drawn from hk to the parabola, right? So if I have a point hk, and if the slopes of the tangents are m1 and m2, then those m1 m2 would be the roots of this quadratic in m, right? Now, what would be the sum of the roots m1 plus m2? K by h. 1. Product of the roots a by h. And this is the condition. Now we have these three things at our disposal, at our service. From these three things, I want to connect h and k. I want to connect h and k, eliminate theta 1 and theta 2. This m1 plus m2 is actually tan theta 1 plus tan theta 2. So I can say, let me write this right here, tan theta 1 plus tan theta 2 This m1 m2 is tan theta 1 into tan theta 2, that's m1 m2. Now we have these three things, this condition and this requirement. Together we will have to stitch a connection between h and k and eliminate theta 1 and theta 2. Okay. Right at the very onset, what's the denominator of this? Cos theta 1, cos theta 2. What's the numerator of this? Sin theta 1, sin theta 2. That means sin theta 1, sin theta 2 divided by mu, because cos theta 1, cos theta 2 is mu. Sin theta 1, sin theta 2 by mu must be a by h. Yes or no? So can I not say that sin theta 1 into sin theta 2 is mu a by h? Can this be said? No? Sin theta 1, sin theta 2 divided by cos theta 1, cos theta 2 is a by h. So denominator is mu, that's given. Therefore this. Now if I do a 3 minus 4, I get a cos theta 1 plus theta 2. If I do a 3 minus 4, I get a cos theta 1 plus theta 2, right? So then 3 minus 4 gives me cos of theta 1 plus theta 2 is what I get. And that must be equal to mu into 1 minus a by h. Now if by some means I could get a sin theta 1 plus theta 2 also, then on squaring and adding the two, I would easily dispense away theta 1 plus theta 2, right? So my next objective is to somehow seek to obtain sin theta 1 plus theta 2 in terms of h and k, and then on squaring and adding, I would be able to eliminate theta 1 and theta 2, right? Okay, now that's no rocket science, because look at this equation 1. Equation 1, if I convert into theta 1 sine and cos, then the numerator would be sine A cos B plus sine B cos A. The denominator would be mu, right? And therefore this would be mu k by h. Yes or no? See, sine theta 1 cos theta 2 plus sine theta 2 cos theta 1. The numerator is sine theta 1 plus theta 2 divided by cos theta 1 cos theta 2, which is mu, equals k by h. Therefore sine of theta 1 plus theta 2 would be mu k by h. Good, that's what we were seeking to do. Square and add 5 and 6. If you square and add 5 and 6, 5 squared plus 6 squared equal to 1. So 1 equal to mu k by h whole squared, this square plus mu squared into 1 minus a by h whole square. And then you generalize, replace h by x and k by y. So when you generalize, you get 1 equal to mu y by x whole squared plus mu squared into 1 minus a by x whole squared. That's the locus of P. That's the locus of P. If a tangent is drawn to the parabola y squared equal to 4ax, this is a parabola y squared equal to 4ax, and if a tangent is drawn to meet the axis in t, there is a tangent drawn at a certain point P, a moving point P. For different t's, you will get different p's. Tangent is drawn, one that intersects the axis of the parabola in t and the tangent at the vertex in y, right? For different p's, you will get different positions of t and y. A is the vertex of the parabola. For every tangent, we take the responsibility of completing this rectangle. We complete this rectangle for every tangent. So for every tangent, there would be a certain g. For different tangents, you will get different g's. We are seeking to find the locus of these g's. Right? Now this is a variable tangent, and therefore t must be treated like a parameter. So the equation of this tangent is yt is x plus at squared. Right? The position of t is obtained by plugging in y equal to 0. So the coordinates of t is going to be minus at squared comma 0. The coordinates of y, if you plug in x equal to 0, you get y equal to 80. So the coordinates of y would be 0 comma 80. Therefore g is going to be, x would be minus 80 squared, y would be 80 for g. Yes or no? Right? So for g, the x coordinate would be minus 80 squared and y coordinate would be 80. What are we trying to do? We are trying to connect the x and the y coordinates of g by eliminating the parameter t. How do I eliminate the parameter t? Y squared is a squared t squared. Right? And then this t squared can be replaced by minus x by a. And that gives us y squared plus ax equal to 0 as the locus of g, which is what? A parabola. So while you draw different tangents, the path that g takes up is a parabola of this kind. Y squared plus ax equal to 0 is a parabola. Yes or no? And it opens like this. This parabola would have vertex same a 0 0, and this parabola would open like this, because x would have to be less than 0 for this to be 0. It would be a leftward opening parabola. Right? That would be the locus of g. Right? 3 is a result that we have dealt with in the class. Right? 4, have I done 4 also in the class? Right? So I have done 4 also in the class. Okay. Let's look at 5. Let's look at 5. So there is a parabola y squared equal to 4ax. And we draw all chords that are normal. Let's say this is a normal at point P. P could be T1, so 8T1 squared comma 2A T1. That's a normal at P, right? Normal at T1. It's going to intersect the other end of the parabola at Q, say T2. A T2 squared comma 2A T2. T1 is a parameter. For every T1 you will have a T2. For different T1s you will have different T2s. So T1, T2 are parameters, right? Now for every normal chord drawn at a variable T1, there is going to be a midpoint M with coordinates h comma k. While you draw normals at different T1s, you get different positions of the midpoint h comma k, and therefore there is a locus associated with M. We are seeking to find the locus of these m's, right? So then there is also a relationship for every normal between T1 and T2. Remember that? T2 is minus T1 minus 2 by T1, right? Now 2h is a into T1 squared plus T2 squared if m is the midpoint. Section formula 1. 2k is 2a into T1 plus T2. Yes or no? Right? From 1, 2 and 3 we wish to eliminate T1 and T2 and connect h and k, and eventually generalize, replace h by k, h by x and k by y to obtain the locus of m, That's what we're seeking to do. Now from this, do you realize that T1 plus T2 is minus 2 by T1? Yes or no? So this second equation could have been written as k into a T1 plus T2 is minus 2 by T1, right? And that brings us to T1 equal to minus 2a by k, right? Now if T1 is minus 2a by k, T2 would be minus T1 minus 2 by T1. So T2 then would be minus T1, which is 2 by k minus 2 by T1. So 4k by a, T2 equal to minus T1 minus 2 by T1. Yes or no? So then we have T1 available, we have T2 available in terms of h and k. All that you need to do is come back to equation 1, put T1 equal to minus 2a by k, oh, k by, I'm sorry, 2, yeah. That's right, k by a. So T1 is this, T2 is this, and all that you need to do is T1 squared plus T2 squared can be plugged in terms of h and k. Use this equation, h and k get connected, generalize that, replace h by x and k by y to get the required locus. In problem 6, we have a point P 14, 7, a point P 14, 7, and from this point, in general, from any point, 3 normals could be drawn to a parabola, right? And the parabola to which the normals are drawn is y squared minus 16x minus 8y equal to 0 is the parabola. We want to find the feet of the 3 normals drawn from this point 14, 7. We want to find the feet of the 3 normals a, b and c that could be drawn to the parabola, right? Y squared minus 16x minus 8y equal to 0. This is the parabola, y squared minus, see, in this case x is a quadratic in y, therefore the parabola would have its axis parallel to the x-axis, right? And from this point 14, 7, 3 normals are drawn. The feet of the 3 normals are ABC. We want to find the coordinates of these 3 points, right? Okay. Now, first of all, what we do is we rewrite this y minus 4 whole squared is 16 into x plus 1. Yes or no? Now, for this parabola y squared equal to 4ax, any point on this parabola is given as x is 80 squared, y is 280. That's a parametric representation of any point on this parabola, right? However, if you have a parabola y minus y1 whole square, this is a parabola with vertex 0, 0. A parabola with vertex x1, y1 would be this, right? Now, any point x comma y on this parabola could be written as x minus x1 is 80 squared and y minus y1 is 280, right? That's what we could do. Then y minus y1 whole squared will become 4 into x minus x1, right? So that's a revision. For this parabola, any point could be written as x is 80 squared, y is 280. However, if this is the form of the parabola, then instead of saying x equal to 80 squared, we say x minus x1 is 80 squared, and therefore y minus y1 is 280. That's the representation of any point on such a parabola. Yes or no? Right? So now on this parabola, which is y minus 4 whole squared is 16 into x plus 1, any point x comma y on the parabola, could be represented as x plus 1. A, in this case, this is 4 into 4. So a is 4, so 80 squared, right? And y minus 4 is 280, means 80, right? A is 4 here, so 280, right? Which means any point on this parabola will have coordinates 40 squared minus 1 comma 80 plus 4 would be any xy would be 40 squared minus 1 and 80 plus 4 would be any point on this parabola. Yes or no? See, x is 40 squared minus 1, y is 80 plus 4 for any point on this parabola, right? Now, the slope of the normal at any xy is given by minus dx dy. minus dx dy would give you the slope of the normal at any xy of the parabola. Minus dx dy. Slope of the tangent at any xy is dy dx. Slope of the normal is minus dx dy, which could further be written as minus dx dt divided by dy dt. Minus dx dt divided by dy dt. Right? Minus dx dt, as you can see, is 8t. If you differentiate this with respect to t, so you get 0 and 8t. Dx dt is 8t, dy dt is 8. So, which is minus t. Slope of the normal at any t is minus t. This is at point t for this parabola, right? The slope of the normal at any t is minus t, yes or no? Right? Now, so far so good, right? Equation of the normal drawn at this point, right? This is a normal drawn at a t given by this. Slope of the normal is minus t. So equation of the normal, this is the normal. Normal is going to be given by y minus 8t plus 4 is slope minus t into x minus 4t squared plus 1. Yes or no? Y minus y1 by x minus x1 equal to minus t. Y minus y1 by x minus x1 is slope minus t. Yes or no? But we are actually talking of a normal that passes through a point P 14, 7. Right? So this normal passes through y equal to 7 and x equal to 14. When I solve for t, I get a cubic in t. There are 3 values of t. Each t will give me one slope of the normal. If you plug in t equal to t1, you get A. If you plug in t equal to t2, you get B. If you plug in t equal to t2, you get C. So then t equal to t1 would give me one set of xy. T equal to t2 would give me B. T equal to t3 will give me C. The feet of the 3 normals drawn from 14, 7 to the parabola. Yes or no? Yes. Right? Okay. So this normal passes through 14, 7. So this becomes 3 minus 8t. Put y equal to 7. So 3 minus 8t equals minus t into 15 minus 4t squared. Put x equal to 14. Right now? So we need to solve for t. So this gives us 4t cube minus 7t minus 3 equal to 0. I need to solve for t from this. Right? Which then will cause the following to happen. Hey, put y equal to 7. So 7 minus 4. 14, 7 passes through this normal, lies on this normal, because it's all, these are all normals drawn from 14, 7. Put x equal to 14, y equal to 7. 7 minus 4. Right? So 4t cubed minus 4t minus 3t minus 3 equal to 0. Yes or no? Or 4t into t squared minus 1 minus 3 into t plus 1 equal to 0. T plus 1, 4t into t minus 1 minus 3 is 0. Right? Or t plus 1 into 4t squared minus 4t minus 3 equal to 0. Right? T plus 1 2t minus 3 into 2t plus 1 is 0. Right? Isn't it? It gives me t equal to minus 1, t equal to 3 by 2 and t equal to minus half. Yes or no? Very good. So plug in t equal to minus 1, you get foot of 1 normal. Put t equal to 3 by 2, here you get foot coordinates of B. Put t equal to minus half, you get coordinates of C. That's how you get the feet of the three normals drawn from these points. Is that okay or not okay? 7 is a reflection property I have dealt with in the class. A line parallel to the axis of the parabola must necessarily pass through the focus of the parabola. Now in problem 8, we are talking about all chords of a parabola PQ that subtend a right angle at the vertex. There are infinite number of PQs that will subtend a right angle at the vertex. Each of these PQs will have a certain midpoint. Each of these PQs will have a certain midpoint h comma k. We want to find the locus of midpoints of all these chords that subtend a right angle at the vertex of the parabola. Clear? Right? The parabola is given to be y squared equal to 4ax. So a is 0 0, the vertex. P is say t1, so a t1 squared comma 2a t1. Q is say t2, so a t2 squared comma 2a t2. Right? I want to connect h and k and eliminate t1 and t2. Yes or no? Right? So first of all, 2h is a into t1 squared plus t2 squared, midpoint. 2k is 2a into t1 plus t2. And there is a condition. The condition that the slope of PA into slope of QA is -1. What's the slope of PA? 2a t1 minus 0 divided by a t1 squared. That is 2 by t1 is the slope of PA. What's the slope of QA? Similarly, 2 by t2. And the product of these slopes is -1. So 4 by t1 t2 is -1. That's the condition. Therefore t1 t2 must be -4. So all that we need to do is using 1 2 and this condition 3, which is t1 t2 equal to -4. We want to eliminate t1 and t2 and connect h and k and then go ahead and generalize. So if I square this, k squared is a squared into t1 squared plus t2 squared, and t1 squared plus t2 squared can be written as 2h by a plus 2 t1 t2. 2 t1 t2 is -8. Yes or no? I hope all of you understand this. When I square this, k squared is a squared into t1 plus t2 whole squared, which is t1 squared plus t2 squared, which is 2h by a plus 2 t1 t2. 2 t1 t2 is -8. Yes or no? Right now? So now I can generalize this. I replace k by y and h by x. So I end up getting a squared in a into 2x minus 8a. Right? So y squared is 2a into x minus 4a. So the locus of the midpoint is this parabola y squared equal to 2a into x minus 4a. Yes or no? Right? The midpoint of all chords that subtend a right angle at the vertex will always lie on this parabola. Right? Y squared is 2a into x minus 4a. Clear? Now the next thing that we want to establish is that these PQs enjoying this property, that means subtending a right angle at the vertex, must be a bunch of concurrent lines. They must pass through the same point on the axis of the parabola. Let's figure out whether it's the axis or some other point. So let me find out the equation of the variable PQ. Y minus 2a t1 is, now what's the slope of PQ? 2a t1 minus t2 divided by a t1 squared minus t2 squared. That means 2 by t1 plus t2 is the slope of pq, right? Now the equation of the variable pq is y minus 2a t1 is 2 by t1 plus t2 into x minus a t1 squared, right? Or y into t1 plus t2 minus 2a t1 into t1 plus t2 is 2 into x minus a t1 squared, right? Minus 2a t1 squared minus 2a t1 squared would get cancelled from both sides, right? And this would give me y into t1 plus t2. See, there is 2a t1 t2, 2a, this t1 t2 is minus 4, so this is plus 8a. When it goes on the other side, minus 8a. Yes or no? I hope you realize what I have done here. 2a t1 t1 gets cancelled with 2a t1 squared, and then 2a t1 t2, this t1 t2 is minus 4 for all these chords, so that makes it plus 8a, going on this side minus 8a, so 2x minus 8a, right? Very clearly this is the variable pq. Why variable? Because t1 and t2 are variables, right? So this is a variable line, pq is a variable line, but realize that if you put y equal to 0 for any point on this variable line, x turns out to be a constant 4a. See, plug in y equal to 0, what is x? 4a. That means this line, if you plug in y equal to 0, x turns out to be 4a. That means all these lines will pass through 4a comma 0. All these lines will pass through 4a comma 0, yes or no? That means all these lines will pass through a certain fixed point on the axis 4a comma 0. I'll tell you, yes, we could have concluded from there also. I was coming to that. All these lines will pass through 4a comma 0. So they are a bunch of concurrent lines. Right from here, realize that the midpoint of all these chords will always pass through 4a comma 0. Midpoint is also a point on PQ. Midpoint is also a point on PQ which always passes through 4a comma 0. Yes or no? That means all the do you realize that? So we could have concluded from here also that these PQs are all passing through 4a comma 0. But just in case you didn't find an opportunity to get that right from here, you could have gone this way and got x equal to 4a comma 0, a point through which this line will always pass, right? Bunch of concurrent lines therefore. Nine is a result we have dealt with in the class. The centroid of the triangle formed out of 3 conormal points will always lie on the axis of the parabola we have dealt with, right? Now, say there is a parabola y squared equal to 4ax. Say there is a parabola y squared equal to 4ax. Okay. And there are a bunch of parallel lines. These are a bunch of parallel lines, each of slope m. Clear? What we do is, at the extremes of these chords, we draw normals. Say this is one sample chord, and I draw a normal at A and I draw a normal at B. Let's say these normals intersect at P, H, comma, K. We are seeking to investigate the locus of these P's. Now, look, for any chord with slope M, let's say this is a chord y equal to mx plus c. Slope m. This is the parabola y squared equal to 4ax. Now if I solve these two equations, I'll get the coordinates of A and B. Yes or no? So this, when I solve these two equations, x can be written as y squared by 4a plus c, which is a quadratic in y. One value of y would be ya, the other value of y would be y of b, right? Y of a and y of b will be the roots of this. The roots of this quadratic would be ya and yb. So m by 4a into y squared minus y plus c is 0. Very clearly, ya plus yb is 4a by m, which does not depend on c, which depends only on m. All these chords have the same m. Therefore, y of this chord plus y of this chord, y of this end of the chord plus y of this end of the chord is 4a by m. Y of this end of this chord plus y of this end of this chord will also be 4a by m. Y of this end of this chord plus y of this end of this chord will also be 4a by m. Yes or no? Yes, independent of the chord? Now. So a sample chord of this family. This is A with y equal to ya. This is B with y equal to yb. I draw a normal at A. I draw a normal at B. These normals intersect at P, which is h comma k. Right? Now, from this point P, a third normal could be drawn. Right? And this third normal would be at some C, which would be y equal to yc. Yes or no? Yes, from this point where the normals intersect, a third normal could be drawn, because in general from a point 3 normals could be obtained to the parabola. Right? Now, A, B, C therefore are co-normal points. So ya plus yb plus yc must be 0. Right? So if ya plus yb plus yc is 0 for 3 co-normal points for a standard parabola, yc turns out to be minus of ya plus yb. That means minus 4a by m is yc. Now, which means what? This is a point C whose y is this. Right? What would the x of this point be? Yc squared by 4a. That means C is a fixed point. Because its y is minus 4a by m, a fixed number, x would be y squared by 4a, a fixed number. Right? So C is a fixed point. Right? Which means, if I take this chord, a certain chord, I draw normals at the extremes of this chord and I obtain a point P. Right? And if I draw a third normal, then the third normal would be always at C. Whether I take this chord, or I take this chord, or I take this chord, or I take this chord, these chords will give me different P's. But the third normal drawn from P, for each of these chords would be at C only. Yes or no? That means, yes, y equal to minus 4a by m for this. That means P will always lie on the normal drawn at a fixed point C. C is a fixed point, and P therefore is always a normal drawn at C. Right? That means all these P's obtained from different chords, different ABs will give me different P's, but all these P's will lie on this very normal drawn at a fixed point C. Therefore these P's are collinear points lying on a fixed normal at C, where yc is minus 4a by m. Yes or no? Got me? Oh, I don't know. You should have. Anyway. Okay, 11 again is a problem like the previous problem. I'll look at 12. I could leave something for you too, right? Find the locus of the middle points of all tangents drawn from points on the directrix to a parabola. Or have you been able to do this? You've been able to do this? No, not all of you are responding in the affirmative. Number 12. Locus of the middle points of tangents. Say this is a parabola y squared equal to 4ax. This is the directrix x equal to minus a. This is a variable tangent. This is a variable tangent drawn at P. For different P's, you will get different tangents. The equation of the variable tangent is yt is x plus at squared. Different tangents will intersect the directrix at different q's, and therefore will have different midpoints. We want to find the locus of M, the midpoint of PQ of all the tangents. That's what we are seeking to do here. Clear? Now, the coordinates of Q. How do I obtain the coordinates of Q? Coordinates of Q could be obtained. Put x equal to minus a for Q. X coordinate of Q is minus a. And the y coordinate of Q is also point on the tangent, right? The y coordinate of Q therefore would be a into t squared minus 1 by t. Put x equal to minus a, you get the y coordinate of Q. That's the y coordinate of Q, right? M is the midpoint of PQ. So can I say 2h is a into t squared minus 1, right? X plus x by 2 is h. And similarly 2k is 2at plus a into t squared minus 1 by t. Yes or no? Yes. What's the parameter here? T. Tangents at different points, right? So different t's. We want to eliminate t here. We want to eliminate t here and connect h and k. Connect h and k. That's what we want to be able to do. Now, see, this gives me, equation 2 gives me 2kt equals 3a t squared minus a. Yes or no? 2kt. Right? Yes or no? So, t squared is 2kt plus a by 3a. That's 3t squared, right? Now in this equation, if you replace this t squared by this, then you get 2h is a into t squared, which is 2kt plus a by 3a minus 1. Yes or no? Right? Now all that you need to do is solve for t in terms of h and k from this equation, linear equation. See, I obtained t squared from this. I plugged into this. I got a linear in t. I can solve for t from this equation. Yes or no? Yes, sir. Once I solve for t from this equation, I can plug into this, that t squared. So t gets eliminated and you get a relationship that connects h and k. That's all. Right? Let's look at 13. There is a parabola y squared equal to 4ax. There is a point T and tangents are drawn from T to the parabola at P and Q. Tangents are drawn, right? Normals at P and Q meet again on the parabola, such as T. Meet at a point, say R on the parabola. We want to find the locus. See, T, P, Q are 3 points. How many circles will pass through 3 points? 1. So for different such T's enjoying this kind of a status, you will have different centers of the circles And therefore we are seeking the locus of the centers of all such circles passing through T, P and Q. You know what I'm saying? See, if P is 8T1 squared 2AT1, Q is 8T2 squared 2A comma T2. What would be T? 8T1 T2, 8T1 plus T2. Yes, yes. Yes, yes, of course. See, normals drawn at T1 and T2 intersect again on the parabola. Therefore, they must subscribe to a condition T1, T2 equal to 2. Yes. Right? Yes or no? Say R is T3. Then 2A T3. That's R. Now, notice this. This is the tangent at P. This is the normal at P. This therefore must be 90 degrees. This tangent, this normal must also be perpendicular to each other. Therefore, what can you say about TPRQ? It's a cyclic quadrilateral. This plus this is 180 degrees. So this is cyclic. Which means a circle passing through T, P and Q must also pass through R. The circle that we are seeking, the one that passes through T, P and Q, must also pass through R, because this quadrilateral is a cyclic quadrilateral. Yes or no? So essentially now we have additional flexibility, that of R. R will be a point on the circle that we are seeking to deal with. Right? Now, one more thing. If R is looked upon as a point, then through this point, 3 normals could be drawn. What are the 3 normals? One at T1, one at T2, and the third one at R itself. Yes or no? Therefore, PQR are 3 conormal points. PQR are 3 conormal points. Therefore, the sum of their T's must be 0. T1 plus T2 plus T3 must be 0. Yes or no? Now, the circle must have TR as the diameter. Why? Because this is angle in a semicircle, right angle. TR therefore must be the diameter of the circle that we are seeking to deal with. The midpoint of TR therefore would be the center of the required circle. So the center of the required circle would be C, the midpoint of TR, H comma K. We therefore need to connect H and K by dispensing away the parameters T1, T2 and T3. Okay, so 2H is A into T1, T2 plus A T3 squared, right? Which is like 2A plus A T3 squared. That's equation 1. 2H is 2A plus A T3 squared, right? The midpoint, x coordinate of the midpoint. 2K would be A into T1 plus T2 plus 2A T3. Right? Hey, T1 plus T2, however, is minus T3. Yes, Sasure. T1 plus T2 is minus T3. So this becomes AT3, because T1 plus T2 is minus T3, 2AT3 minus AT3, which is AT3. So T3 therefore becomes 2K by A. Yes or no? Plug T3 in this equation. Right? The last rights to be performed. 2H. Equation 1, 2H is 2A plus A T3 squared, which is 2K by A whole squared. Replace H by X and K by Y. So you get X equal to A plus 2Y squared by A, or Y squared equal to A by 2 into X minus A. Yes or no? Which is a parabola, right? Right. Now look at the, I want you to look at the next problem, which is, I want you to look at 15, because 14 I have dealt with in the class, if you remember, right? Please start attempting 15. So there is a parabola C1 which is x squared is y minus 1. This is a parabola whose axis is x equal to 0. That means the y axis is the axis of this parabola. There is another parabola C2 which is y squared is x minus 1. The axis of this parabola is y squared equal to 0. That means the x axis. The vertex of this parabola is 0 comma 1. The vertex of this parabola is 1 comma 0. Right? X squared equal to y minus 1 is this parabola. C1 x squared is y minus 1. Vertex being 0 comma 1 is the vertex. Right? And obviously y has to be greater than or equal to 1. That's why it opens upwards. Right? This parabola is y squared equal to x minus 1. This is C2, which is y squared equal to x minus 1. Is this parabola, right? Vertex of this parabola is 1 comma 0. Now one thing, a result that we covered when we were doing straight lines. This is a line y equal to x, right? If there is a point, P h comma k, if there is a point P h comma k, then the reflection of this point about the line y equal to x would be P prime, which would be k comma h. That means x and y are interchanged. You get the reflection of a point about y equal to x. Yes or no? Yes, right? Right? I said if there is a point, say 2 comma 3, its reflection about y equal to x would be 3 comma 2. That's a standard result in straight lines. Right? X and y coordinates get swapped. Right? Similarly, look at this. This curve can be obtained from this curve by replacing x by y and y by x. The two curves can be obtained from each other by interchanging x and y. Yes or no? Therefore, the two curves must be reflections of each other about the line y equal to x. Yes or no? Right? Which means, say if this is y equal to x, then this curve C1 and C2 are mirror images of each other about y equal to x. Right? If I look at any point A on this curve and I draw a line perpendicular to y equal to x, then B would be the mirror image of A, where this object distance will be equal to this image distance. And the line joining the object and the mirror would be, object and the image would be perpendicular to the mirror. That's a property of reflection, right? Okay. Now, P be any point on C1. P be any point on C1, right? And Q be any point on C2. This is C2. Any point on C2. P1 and Q1 be the reflections of P and Q about the line y equal to x. So the reflection of P about the line y equal to x. The reflection of P must lie on the curve 2. P1 must lie on curve 2. Yes or no? the reflection of any point on this curve must lie on this curve, because the two curves are mirror images of each other, right? Where, say, PM1 would be equal to MP1, and the line joining P and P1 would be perpendicular to y equal to x, right? Now, Q1 be the reflection of Q about y equal to x. The reflection of Q on C2 must lie on C1. The reflection of Q is Q1, which must lie on C1. Clear? Again, M2 is the midpoint of QQ2 such that Q1 M2 must be equal to M2 Q. Object distance must be equal to image distance, and this must be perpendicular, right? Now we want to show that the first part of the problem, that P1 lies on C2 and Q1 lies on C1, is evident because the two are mirror images of each other. That's the first part of the problem, which is already taken care of. The next part of the problem is we want to show that PQ for any P and Q, PQ is larger than minimum of the two numbers PP1 and QQ1. PQ, the length of the line joining a point P on C1 and a point Q on C2, must be larger than the smaller of PP1 and QQ1. Between these two numbers there is one which is smaller. PQ will be larger than these two, where PP1 and QQ1 are perpendicular to the line y equal to x. Now, this is PQ. Let me say this point is T. Right? Can I say PT must be greater than PM1? Hypotenuse bigger than the perpendicular. But what is PM1? PM1 is half of PP1, yes or no? PM1 is half of PP1. Right? Similarly, QT, right? QT must be greater than QM2, right? Hey, but what's QM2? Half of QQ1? Yes or no? Yes. Let me add these two. PT plus QT, extremely QT. That's PQ, right? PT plus QT is PQ, right? Add these two. PQ greater than half of PP1 plus QQ1? Yes or no? Right? If I add these two, this is what I get. Now, PQ therefore is greater than the average of PP1 and QQ1. Is greater than the average of PP1 and QQ1. Hey, but the average of two numbers will be greater than the smaller of the two numbers, right? That means this is greater than the smaller of the two numbers. The average of two numbers will be greater than the smaller of the two numbers, but will be smaller than the greater of the two numbers. Isn't it? Yes, sir. So PQ greater than the smaller of PP1 and QQ1. That fact. Yes or no? Yes, sir. Which means now this brings us to something extremely important. So far so good, right? No issues with this. Now, see, these are the two parabolas, mirror images about y equal to x, right? There are many points P that I can select on this. I can select a point Q on this. For different PQ combinations, I get different lengths of PQs, right? I take a point here and a point there and I get a PQ and I get a length PQ, right? So I can get infinite sets of PQs between the two curves, right? I'm seeking to find the smallest of all the PQs that I ever could get by selecting a point P and a point Q. You know what I'm saying? Now, one thing that becomes pretty evident from this, see, there are two kinds of PQs that I can get. This is the line y equal to x, right? Y equal to x. There is a PQ that could be perpendicular to the line y equal to x, and there could be a PQ which is inclined to the line y equal to x, right? One thing for sure, the perpendiculars, see, because PQ is the inclined PQ, will always have a PP1 or a QQ1 which is smaller, isn't it? The inclined PQ, for an inclined PQ, I can find a PQ here or a PQ here which is smaller than PQ. See, I could have had a PQ like this, a PQ inclined, and a PQ like this. So there are three PQs, two perpendicular and one inclined PQ. Of these, three different PQs, right? There is a PQ here, for example, there is a PQ here, and there is a PQ here. These are two perpendicular PQs. The smallest of these three would be the one which is perpendicular, because PQ is greater than the two perpendicular PQs. These are the two perpendicular PQs, and of them, PQ will always be smaller than this or this. PQ will always be larger than the smaller of these two. Yes or no? PQ will be larger than the smaller of these two? Yes or no? Right? That means, in no case of all the PQs will the inclined PQ be the smallest. If there is a PQ which is the smallest, then that PQ must be perpendicular to y equal to x. Of all the PQs that I can create, of all the PQs that one could create, a PQ which is perpendicular to y equal to x will be the smallest PQ. Yes or no? Right? So, this parabola and this parabola is x squared equal to y minus 1. This parabola is y squared equal to x minus 1. Of all the PQs, this PQ will be the shortest, the one which is perpendicular. But again, amongst these perpendicular PQs, we can have many perpendicular PQs. Of all these perpendicular PQs, we want to find the smallest PQ. That will be the smallest of all PQs. Right? Okay. So, suppose this P is x equal to alpha, then y would be alpha squared plus 1, isn't it? On this curve, what is this curve? This curve is x squared equal to y minus 1. So, x of this point suppose is alpha, then what would be y? Alpha squared plus 1, isn't it? Just see, let's see, we'll figure out. If x is alpha, y would be alpha squared plus 1 for this point P, yes or no? Yes, sir. X is alpha, put x equal to alpha, so y becomes alpha squared plus 1. Q is the mirror image of P, because PQ is perpendicular to the line y equal to x, so P and Q are mirror images of each other about y equal to x. So Q would be alpha squared plus 1 comma alpha. X and y get interchanged. Yes or no? Now, we want to model alpha for PQ to be the smallest, right? What is PQ squared? Distance formula if I apply, that's twice alpha squared minus alpha plus 1 whole squared. Distance formula? x2 minus x1 whole squared plus y2 minus y1 whole squared. Right? Yes or no? Yes, so then, PQ will be the smallest when alpha squared minus alpha plus 1 will be the smallest in magnitude. Yes or no? PQ will be smallest when alpha squared minus alpha plus 1 becomes the smallest, and let's find the value of alpha for which this becomes the smallest it could. This could be rewritten as alpha minus half whole squared plus 3 by 4. This expression alpha squared minus alpha plus 1 is this? Yes or no? Which is always greater than or equal to 3 by 4? Because this is always greater than or equal to 0. So this will be always greater than or equal to 3 by 4, yes or no?
Yes, sir.
That means the minimum value of alpha squared minus alpha plus 1 is 3 by 4. And this happens at, it will become equal to 3 by 4 for alpha equal to half. This happens at alpha equal to half. Right? So when alpha is half, what is P? P would be half comma 5 by 4. Q, the mirror image of this, would be 5 by 4 comma half. Such would be the coordinates of P and Q for PQ to be the smallest it ever could. Got it? Very good. Right then, refer to the remaining problems of the sheet on parabola. The 16th problem. So this is a circle, and this is a parabola, and we want to find all common tangents between them. Now, any tangent to this parabola must be of the form y equal to mx plus a by m. A is obviously 1/4 for this. Now, for this line to be a tangent to the circle as well, the distance of this line from the center of the circle must be equal to the radius of the circle. The center and radius are these. Now, distance of this line from the center equal to root 5 is this statement really, right? And therefore, all that we need to do is to solve for m. Find all possible values of m. Different m's when plugged into this, commensurate with this condition, will give me different tangents, common tangents between the circle and the parabola. That's what, right? So, now it's merely algebraic. Let's see how to solve for m given this. Okay. So then we have like a 12m minus 3 whole square 16,580 into m square plus 1. Right? This is what we need to solve. Into m squared. 16m squared into m square plus 1. Clear? So this gives me like a 80 m to power 4 minus 64 m squared plus 12 m minus 1 minus 1, right? So plus 24 m minus 1 equal to 0. That's the equation. Right? That's the equation. Yes or no? Right? Fourth degree polynomial in m, right? It's going to take quite a bit of us to solve this. But what we'll do is, see what's causing problem is these bulky coefficients, right? These bulky coefficients are really causing an issue. Let me reduce the bulk of these coefficients first and then examine it from that point onwards. Okay. 2m 16 5 minus 2m 4 16 plus 12 2m minus 1 equal to 0. Right? At the very onset, let me take 2m equal to some t. I have reduced the bulk now, 5, 16 and 12. These are manageable coefficients. Okay. So then I end up getting 5t to power 4 minus 16t squared plus 12t minus 1 equal to 0. Right? So I need to solve for t. Each value of t will give you a corresponding value of m, given 2m is t. So one root by inspection, as you can see, 1 minus 11 minus 12, t equal to 1 is a root. Do you see that by inspection? If you put t equal to 1, 5 minus 16 minus 11 plus 12 plus 1 minus 1, 0. T equal to 1 is a root obtained by inspection. Yes or no? Yes, that means t minus 1 must be a factor of this. T minus 1 must be a factor of this. Therefore, what we do is, we do a synthetic imposition of t minus 1 in this expression. See, this is 5t to power 4 minus 16t squared plus 12t minus 1 equal to 0. We just want to factorize this, isn't it? I know that t minus 1 is one of the factors, right? So 5t cubed into t minus 1 minus 5t plus 5t. So plus 12t. Okay, 5t squared, 5t cubed into t minus 1. So minus 5t cubed plus 5t cubed. Do you realize what I am doing? Yes, see, t equal to 1, all that I am doing is, I am imposing a factor t minus 1 in it. So t minus 1, so 5t cubed, and this t minus 1, right? And then minus 5t cubed, so plus 5t cubed. So plus 5t cubed, I do a 5t squared into t minus 1, so that the plus 5t cubed comes in. Then minus 5t squared, I add plus 5t squared, minus 16t squared, so minus 11t squared. So minus 11t, and then again a synthetic imposition. And then I have done a plus 11t, I do a minus 11t. So that will become t minus 1 as the last factor, last term, equal to 0. I hope you realize what I have done here. 5t cubed minus 5t cubed. I brought this from outside, but I managed it here. Clear? So now I take a t minus 1 common. 5t cubed plus 5t squared minus 11t plus 1 equal to 0. Right? So far so good? Now let me factorize this. And 11. So t equal to 1 is also a factor of this. So again I can impose a t minus 1 factor into this. So t minus 1, 5t squared into t minus 1 minus 5t squared. So I add a plus 5t squared, that will make it 10t squared. So plus 10t into t minus 1 minus 10t, so plus 10t. So minus t, so minus t minus 1 equal to 0. Yes or no? So that makes it t minus 1 whole square into 5t squared plus 10t minus 1 equal to 0. It will give me 4 values of t. 2 coincident values of t, 1 comma 1 from this. And when you solve this quadratic using Sridhar Acharya, you will get 2 other values of t. And for each value of t, you get a corresponding m. And then for each m, there is a tangent y equal to mx plus 1 by 4m is the tangent. Yes or no? Right? So you end up getting 4 tangents, out of which 2 will be coincident. T equal to 1 will give me 2 coincident tangents. T equal to 1 would give me m equal to half. So a tangent with m equal to half, mx plus 1 by 4m, will be like 2 coincident tangents. And the other 2 values of t would give me 2 distinct values of m, 2 more tangents when plugged into this. 4 tangents in all, 2 coincident and 2 distinct. Right? Got me? Okay, 17. Your attention, please. If a squared greater than 8b squared, the problem says if a squared greater than 8b squared, then there exists a point such that the 2 tangents drawn from y squared equal to 4ax, from that point, the 2 tangents drawn from a point to this parabola y squared equal to 4ax are normals to parabola x squared equal to 4by. We want to show that if a squared greater than 8b squared, then there will exist a point from where, when you draw the 2 tangents to the parabola, they would be normal to those two tangents would be normal to this parabola given a squared greater than 8b squared, right? Hey, first of all, let me start with y squared equal to 4ax. Any tangent to this parabola must be of the form y equal to mx plus a by m, right? Suppose the tangents that we are talking about pass through h comma k. That means this tangent passes through h comma k. We want to show that there exists a point h comma k from where when you draw tangents, then those two tangents will be normal to that parabola. Yes or no? Given a square greater than b square, existence of such a point is guaranteed if that happens, right? Now, so h comma k will satisfy this equation. So k equal to mh plus a by m, or we have so leave it here. Now realize that any normal to this parabola, this parabola x squared equal to 4by, let me look at a generalized normal to this parabola, right? And then say that the normal that we obtained is identical to this tangent. When would the normal obtained from there be identical to this tangent? That condition must be a square greater than 8b squared. The normal here identical to the tangent there, provided a square greater than 8b squared for a certain h comma k, right? Then h comma k exists, is guaranteed. Now x squared equal to 4by, any point on this is x equal to 2bt, y equal to bt squared, right? In y squared equal to 4ax, you have 80 squared 280. In this, you will have x as 2bt, y as bt squared, right? Now, any point on this? So, any point on this parabola is like x is 2bt, y is bt squared, right? So, if I am talking of a point P referred to as t on this parabola, then this is the normal. The slope of the normal at any given point P would be minus dx dy. Minus dx dy is the slope of the normal, right? Minus dx dy means minus dx dt divided by dy dt. That's the slope of the normal at any point, right? Minus dx dt means minus 2b, minus dy dt means 2bt, that means minus 1 by t would be the slope of the normal. For this parabola, Bolo, Shashi, you have a question, please ask. This x is 2bt, slope of the tangent is dy dx, this dx dt, dx dt is 2b, na? Dx dy is dx by dt by dy by dt, that's chain rule. And dx dt is what? Dx dt is 2b, dy dt is 2bt, differentiating. The slope of this normal is minus 1 by t. Therefore, the equation of this normal is y minus bt squared is minus 1 by t into x minus 2bt is the equation of this normal. That's the equation of the normal. Therefore, we have like a y equal to minus 1 by t into x plus bt squared plus 2b. That's the equation of this normal at some t, right? At some t given by 2bt comma bt squared, any point on this, that's the equation of the normal, right? Now, what you want is, this is y equal to some slope into x plus c. That's a form. What you want is this normal to be identical to this tangent. You want a condition for which 1 is identical to 2. This normal identical to this tangent. Now, do you realize it will happen if m is minus 1 by t, it will happen for 1 to be identical to 2, m would be minus 1 by t, right? And a by m would be equal to bt squared plus 2b, and t must be real. T must be real, right? This is condition A, condition B, right? M minus 1 by t, the constant term a by m equal to bt squared plus 2b. Then the two lines would be identical. The tangent there would be a normal there, right? A by m is actually minus at, because 1 by m is minus t. So minus at is bt squared plus 2b, right? Or bt squared plus at plus 2b equal to 0. But t is real. Existence of such a point p is real. Therefore t must be real. So discriminant must be greater than 0. Therefore a squared minus 8b squared must be greater than 0, or a square greater than 8b squared. Right now? Make sense? Okay. Let's look at the next one. 18. Find the condition so that the parabola y squared equal to 4b into x minus c and y squared equal to 4ax have a common normal other than the axis. See, in both cases the axis is y squared equal to 0, the x axis is the normal. That's a common normal, but if we want a normal other than the axis, common normal other than the axis, we want to find a condition. Have a common normal other than the axis, Yes or no? Now, any point on this parabola is 80 squared comma 280. That's any point on this parabola. X is 80 squared, y is 280. And as we have seen before, the slope of the normal at any t would be minus t for this parabola, standard parabola. So I'm not revisiting that situation. So then the equation of the normal at p is y minus 280 is minus t into x minus 80 squared. Right? That means y is minus tx plus 80 cubed plus 280. That's the equation of the normal at any t for a point p. At a point p, that's the equation of the normal at a point p. Right? Now, let me look at a point q on this parabola. Now, any point q on this parabola is x minus c is bt squared and y is 2bt, isn't it?
Yes, sir.
That's a revised parametric condition. X minus c is bt squared and y is 2bt. Any point on this. That means any point on this is like x equal to c plus bt squared, y is 2bt. Any point on this parabola, right? Right? Now, let me look at a point q of on this, which is t equal to t1. Let me look at a point q which is t equal to t1. I mean, why do you assume that this t and this t will be the same? They are different points. The normal here will be the same as the normal there, but they would be different t's, right? So the normal at any t equal to t1. First of all, what's the slope of the normal at any xy? Slope of the normal at any xy is minus dx dy, which is like minus dx dt divided by dy dt. That's the slope of the normal at any xy. Minus dx dt is like minus 2bt divided by 2b, which is minus t. So if I look at a point T1, what would be the slope of the normal at T1? Minus T1. What would be the slope of the normal at T1? Minus T1. What would be the point Q? The point Q would be, x would be C plus BT1 squared, C plus BT1 squared, y is 2BT1. That would be the point Q. The slope of the normal at this point is minus T1. Therefore, the equation of the normal at Q is y minus 2BT1 is minus T1 into x minus this, x minus C minus BT1 squared. Yes or no? That's the equation of the normal at t equal to T1 of this parabola, right? Which means or y is minus T1x plus CT1 plus BT1 cubed plus 2BT1. Yes or no? See, minus T1x plus CT1 plus BT1 cubed and plus 2BT1. That's the equation of the normal at T1 of this. Now, what we want is, for some combination of T and T1, this normal should be identical to this normal, then the two normals would be the common normal. This would be a normal at P of this parabola, this would be a normal at Q of this parabola, but if this line is identical to this line, then they would represent a common normal to the two parabolas. Yes or no? Yes, sir. Right? So what we are seeking is 1 identical to 2. That's what we are seeking, 1 identical to 2. Now, if this line is identical to this line, very clearly T equal to T1, right? This would give me T1 equal to T. And equating the constant terms, we get CT1 plus BT1 cubed plus 2BT1 is like a AT cubed plus 2AT, equating the constant terms. See, the constant term here is CT1 plus BT1 cube plus 2BT1. The constant term here is AT cube plus 2AT. Right? Now, replace this T1 by T, for example, or T by T1, because T and T1 are identical. When we attempt to compare the two equations for them to be identical, right? T equal to T1 means, let me drop this subscript because T and T1 are the same now. Now I can divide by T because T is not 0. T equal to 0 will represent the vertex. That's the axis of the parabola. The normal drawn at the vertex will be the axis of the parabola. That's a common normal for sure. But that's not the normal that we are seeking. We are seeking a normal other than the one happening at T equal to 0. T equal to 0 will be the vertex. And the axis of the parabola is the normal at the vertex. In this case, they have a common axis. So that's the common normal. But we are not seeking that normal. So T equal to 0 is ruled out. T equal to 0 is ruled out. And therefore, dividing by T is legitimate. Because T is not 0. T equal to 0 will give me the vertex, and therefore, the normal at the vertex, which is the axis of the parabola. We are not seeking that normal. Right? Yes. So let me divide by T. When I divide by T, CT is 2B. This is what I get. Right? Or A into, or A minus B into T squared must be C plus 2 into B minus A, right? Divide by A minus B, so T squared is C by A minus B minus 2, right? But T is a real number, not 0, so T squared must be greater than 0. T squared must be greater than 0, this must be greater than 0. Because T is a real number, right? And therefore, the required condition is C by A minus B greater than 2 is the required. So then, the next problem, there is a parabola and the parabola will have an axis, which is the axis of symmetry of the parabola, right? we want to establish that there exists a point K on the parabola. There exists a point, a fixed point K on the parabola, such that if you attempt to draw a chord passing through K, any chord, how many chords will pass through K? Infinite chords pass through K, right? K is a fixed point. We want to show the existence of a fixed point K. We want to establish the existence of a fixed point K such that any chord passing through this will have the following property: 1 by pk squared plus 1 by qk squared is a constant. That means for any chord passing through this, 1 by pk squared plus 1 by qk squared must be a constant. Exists such a point. There exists such a point. Okay. There would be no loss of generality if I assume the parabola to be y squared equal to 4ax. Right? Then the point K would be like some K0, a fixed point K, K0. Right? Say different lines passing through K will subscribe to different values of theta. Theta is a parameter, right? Different lines will have different theta. Now what's the slope of PQ? Tan theta. If this is my choice of theta, then the slope of PQ would be tan theta. Yes or no? For a standard parabola, right? Now, any point, suppose there is a point K0. Any point on this line can be written as, say, this distance is r, suppose. Km is r. This is a reference point. And if this distance is r, then any point on this line can be written as k plus r cos theta, 0 plus r sin theta, 0 plus r sin theta. Parametric form of the equation of a line. X is h plus r cos theta, y is k plus r sin theta. At a distance r, mod r will represent km. Mod r will represent km. Remember the parametric form? Right. Now, if this point M, by its very design, it's a point on this line. But now, if it's also a point on the parabola, then it will satisfy the equation of the parabola, right? So if M also lies on the parabola, it will satisfy the equation y squared equal to 4ax. It will satisfy this equation. That means the coordinates of M, x coordinate is this, y coordinate is this. So this gives me r sin theta whole square equals 4a into k plus r cos theta. Yes or no? When you solve for r, you would get the r of the point of intersection between the line and the parabola, because M lies on the line as well as lies on the parabola. Yes or no? So when you solve this equation, a quadratic in r, you will get the r for the points of intersection of the parabola with the straight line. You would get the r of the intersection points of the parabola with the straight line. That's what you will get. Yes or no? You get a quadratic in r. So when you solve for r, what will you get? You will get r equal to r1 for p and r equal to r2 for q. r1 and r2 will be the roots of this quadratic. Yes or no? Where mod r1 would be pk and mod r2 would be qk. Right now? So this equation has roots r1 and r2, where mod r1 is pk, mod r2 is qk. Clear? So then this equation rewritten, r squared sine square theta minus 4a cos theta into r plus 4ak minus 4ak is 0, has roots r1 and r2. Right? Where what is r1 plus r2? 4a cos theta by sine square theta. What is R1 R2? Minus 4ak by sine square theta. That's R1 R2. What we are seeking is the following. We want 1 by pk squared plus 1 by qk squared to not depend on theta. We want 1 by pk squared plus 1 by qk squared to not depend on theta, and therefore to have the same value for all theta. That's what we are seeking. Such should be the premise of k, right? That means this, which is the same as 1 by r1 squared plus 1 by r2 squared, we want this to be independent of theta. We want this to be independent of theta. This is the point k that we are seeking. Yes or no? Right? Now 1 by r1 squared plus 1 by r2 squared, that means r1 squared plus r2 squared by r1 squared r2 squared, that should be independent of theta. Such should be the point k. But what is this? This is like a r1 plus r2 whole squared minus 2 r1 r2 divided by r1 squared r2 squared. That should be independent of theta. Such should be k. Such should be k, right? Which means r1 plus r2 whole squared, which is like a 4a cos theta by sine square theta whole squared minus twice r1 r2 means 8ak by sine square theta by r1 r2 whole squared means 16a squared k squared by sine to power 4 theta. This should be independent of theta, right? This should be independent of theta. This is what we are seeking to do here, right? Right. So now if I multiply by sine square theta, so I have like a 16a squared cos square theta plus 8ak sine square theta. This should be independent of theta, right? Hey, one thing by inspection. If you plug in k equal to 2a, you have 16a squared cos square theta plus sine square theta, which will become independent of theta. If all that I'm saying is, if you took k equal to 2a, this will become 16a squared sine square theta plus 16a squared cos square theta. That will be 16a squared independent of theta. That's by inspection. But suppose the inspection factor didn't occur to you, right? Then what you do is, this you can write 16a squared cos square theta plus 8ak. This sine square theta you can write as 1 minus cos square theta. This you want to be independent of theta, right? Or you have like a 16a squared minus 8ak cos square theta plus 8ak to be independent of theta. Hey, 8ak is anyways independent of theta, so you want this to be independent of theta. Now for this to be independent of theta, this must be 0. You know what I'm saying? This entire expression ought to be independent of theta. 8ak is anyways independent of theta. Don't have to bother about it. That means this must be independent of theta. For this to be independent of theta, this 16a squared minus 8ak must be 0. Then it will become independent of theta, right? Yes or no? Right? So we must have like a 16a squared minus 8ak is 0, or k must be 2a. So if you have a point 2a comma 0, then any chord passing through this would enjoy the property 1 by pk squared plus 1 by qk squared equal to constant. Same for all chords means same for all thetas. That means independent of theta. Got me? You have a question. I want to address that. Please ask. Come from? Where did it come from? Oh. No. Okay, look. See, we want this ratio to be independent of theta. Sin to power 4 theta goes up. So this is anyways independent of theta. Therefore, if the ratio has to be independent of theta, denominator is anyways independent of theta when this sine to power 4 theta goes up, then the numerator should be independent of theta. See, when I multiply by sine to power 4 theta, this will be the numerator of this expression. The denominator then would be left with 16a squared k squared, which anyways would not have any theta. So all that you want to do is you want to bleed theta out of the numerator. Such should be your choice of k. So this was the numerator on multiplying both numerator denominator by sine to power 4 theta. Right? Message sent. All of you understand this then? This then brings us at least to a formal conclusion of parabolas, right? But then following every formal conclusion, you have a lot of work. There was a test scheduled today, but then I made it tentative so that for those of you who get some butterflies in the tummy because there is a projected test, would come prepared. To create butterflies in the tummy, I announced a tentative test so that you could at least come, and the fear of the sword of Damocles hanging over you, that there could also be a class, a new topic started, would kind of compel you to be very confused about what the agenda would be. Therefore, it will force you to come for the class, prospective new theory, new topic, and therefore also be prepared, because I could also act wicked. Right? But then of course, if you are prepared today, then you will be better prepared on Wednesday. Right? Because if you've come prepared, you always thought, hey, I wish I had another day. Right? So now you have 3 more days. Huh? No, I would keep no, please. You can allow all that for me to decide. So, Prakhar, I'll only allow you to ask questions, good, bad or ugly. No, most of the time. Okay, we'll refrain from that commentary. But come prepared, because on Wednesday, reason I also chose to finish the sheet on thermodynamics? Yes. I thought it would be unjust to include thermodynamics without finishing that sheet. Okay. So then, yes, come prepared with thermodynamics as well. And I'm not ruling out the possibility of quadratic equations getting started on Wednesday. All right.